Hi guys, and welcome back to my channel. In this video I want to go over radicals and carbocations. So firstly, we've already sort of discussed what radicals are and carbocations are in the odd Lewis structures video, and we talked about how we can draw these Lewis structures and how they're a little bit weird. They don't have octets, or they have unpaired electrons, or they're weird Lewis structures. They're not what we normally see. In this video, I want to discuss more about the reactivities of them and what stabilizes a radical or what stabilizes a carbocation. So what do they even have in common, right? We talked about these in our odd Lewis structures video. So they're odd, right? Odd in terms of the Lewis structure. And secondary, or second, what's similar between these is that they're very unstable, right? These are both very high energy products, right? Both radicals and carbocations are very, very high in energy, and they cannot be isolated. So this is another thing, right? You won't have radicals or carbocations being the product of a reaction. You'll have them as intermediates in a reaction. So these are just some things I want you to keep in mind as why are we talking about radicals and carbocations together? They're very unstable, high in energy, right? High in energy. They can't be isolated, right? You can't just have a jar of radicals or a jar of carbocations, or a beaker of radicals or a beaker of carbocations. They're intermediates in reactions. So that's why I want to discuss these two together and discuss their stability and discuss their reactivities together. Okay, so now I want to talk about radical initiators, and when we talk about initiators, right, initiating something means to start something. So a radical initiator is going to start a radical reaction by forming radicals. So we're going to take, a normal, stable-ish molecule, and we're going to react it, or we're going to have some reaction occur that takes that normal-ish molecule that's lower in energy and forms a radical that's very high in energy. So let's look at the two sort of big groups of radical initiator reactions that I've outlined here. So this first group I just call like bond breaking homolytically. So this is just bond breaking homolytically. And these are where you just have a bond that breaks, and the bond gives one electron to one atom and the other electron to the other atom. And so now we have two unpaired electrons on two different atoms, right? And that's what a radical is. A radical is just an atom with unpaired electrons, or a compound with unpaired electrons. Now, the next general category is where we, again, form radicals, but a gas is emitted. Gas emitted. And we'll talk about why gas emitted, just as when a gas is emitted, this causes a huge increase in entropy. And this increase in entropy, right, because gas is much more disordered as a phase than whatever, a liquid or a solid. So whenever you produce gas from a liquid or a solid, you're getting a massive increase in entropy. And this increase in entropy causes the delta G of the reaction to become very low, or almost negative, right? The delta G is equal to delta H minus T delta S. And in these reactions where we form radicals, we're still breaking bonds, so our delta H is most likely going to be positive, right? Because our enthalpy change, we have to use energy to break bonds. But our delta S, when we release gas, is very positive. So this term will make delta G negative, and it's going to drive the reaction. It's going to drive the reaction to completion, right? So basically, when we have a gas emitted, we can form radicals because even though the radicals are unstable, our entropy change by releasing gas is very high, and that's going to cause our delta G to become, negative. Okay, so let's go back to the top. Radicals are formed by cleaving weak bonds, and that just means breaking the bonds homolytically so that each atom gets one electron. That's sort of what I talked about in our first general category. So let's look at the first category in more detail. So two common radical initiators are peroxide and halogen bonds, and these are just weak bonds that have low bond dissociation energies. So basically we don't need that much energy to break the bond, and so it's slightly easier to form radicals from these initial, from peroxides and from halogens. So you can see these arrows I've drawn where I have this bond between a peroxide, right? In your peroxide you have the OO single bond, and I drew fishhook arrows, right? These red arrows are called fishhook arrows. So I'm going to just write here, our red arrows are fishhook arrows. And what fishhook arrows mean is that there's only like one little, like they're not double-headed, right? They're not like that. They're instead like with one head. And that means that denotes a movement of one electron. And because we're looking at bond association, homolytic bond association, that means each atom is getting one electron, so we need two arrows to denote one electron moving from the bond to one atom and the other electron moving from the bond to another atom. So that's why we use fishhook arrows in these radical reaction mechanisms. So fishhook arrows denote movement of one electron. Okay. And we use normal double-headed arrows like these, right? We use these normal double-headed arrows to denote the movement of a pair of electrons, and that's what we use in most reactions. Like when we have a nucleophile attacking an electrophile, we have a lone pair of electrons going and attacking the electrophile, right? Okay, so this is one category of cleaving bonds where we have peroxides, just you're breaking the OO bond and you're giving each oxygen an electron, or halogens where you're breaking, for example, the Br-Br bond or I bond or Cl-Cl bond, and each halogen gets one electron. And you can see our conditions for these reactions is either light or heat, and that just means that we need a little energy in order to break the bond, right? We need to enter a little input a little energy into the system to break these bonds and create radicals. Okay. So now let's look at the second category where we have gas emitted. These bonds are broken. Bonds are broken easily where gas is emitted because, as I said before, the increase in entropy will drive the reaction. So let's look at two common sort of radical initiators. We have this guy, which is called a azo compound. This general term for a compound with this N-N double bond, this nitrogen-nitrogen double bond, is called an azo compound. And you can see with the arrows I've drawn, right? You see with these arrows I've drawn, it forms nitrogen gas and two radicals, where these are the radicals. And yeah, so pretty clearly you can see I'm taking one electron from each of these bonds and making it a triple bond in the nitrogen. And I'm taking the other electron from that bond and putting that as a lone electron, which creates the radical. So that's how we have, and this release of nitrogen, right? Nitrogen is a gas, N2 gas, is what drives our reaction forward. So azo compounds with a little bit of heat, you're going to break those bonds. You're going to break those the bonds between the nitrogen and the carbon here, and on the other side as well. And you're going to form nitrogen gas and two radicals. The other option, right, the other way to form radicals is by using nitrites. So these are nitrites. Not this, but this compound here is called, the general term for it is a nitrite. And again, you can see with the fishhook arrows I've drawn, you're taking one electron from the bond, putting it on the nitrogen, taking the other electron from the bond, putting it on the oxygen, and you form nitrogen monoxide. Nitrogen monoxide is a gas, so this increase in entropy by forming a gas is going to drive this reaction to completion, and you form this other radical. Right? So hopefully and you can see the conditions of these reactions are always light or heat because you need to input energy. You need to input energy to break bonds, right? You always need a little bit of energy in order to break bonds. So why do we use these radical initiators, right? Say I don't want to create, say I have a radical reaction, but I want to use a different radical than the ones I've created, right? but maybe that radical is not easy to make right away. Like maybe there's no radical initiator that automatically creates the radical I want. How can I use these radical initiators to eventually create the radical I want, right? These compounds basically can start radical reactions. It's easy to break these bonds and form radicals. These formed radicals, so all of these guys, right, that are easy, it's easy to form these guys. And these radicals can then react with other molecules to create other radicals, which can then participate in reactions maybe we want. So in this video, we're going to talk about a simple but very useful reaction called radical halogenation. I'll just write it here, radical halogenation, and I'll talk more about this when we get to that slide. But basically, it's very useful in organic chemistry because you're introducing with this reaction a functional group into a complex molecule. So yeah, so hopefully this gave you an idea of why we use radical initiators and why some things are better as radical initiators than others. Either radical initiators have weak bonds, or they release gas when forming the radicals, and that drives your reaction to completion. We can then use these radicals to form other radicals, and those radicals are the ones we might want to actually react in a certain reaction. So we talked about formation of radicals. Now I want to talk about formation of carbocations, right? As we said, none of these things can be isolated, right? We can't just have a jar of radicals or a jar of carbocations. They're all very, very high in energy. And what that means is we don't form radicals or carbocations. We don't have them like prepared, right? We need to form them somehow. So we talked about how there's radical initiators to form radicals. Let's talk about how we can form carbocations and why they form, right? And the one key way we form carbocations is the loss of a leaving group. So let's talk about that, right? A leaving group is a group that is very stable. When it grabs electrons from the bond it has to carbon and leaves, right? As the name implies. So this can be thought of as heterolytic bond dissociation. So we talked about homolytic bond dissociation. Homolytic bond dissociation with radicals is where both atoms get one electron from the bond. Heterolytic bond dissociation is where one atom gets both of the electrons from the bond. So you can see how they're a little bit different. So let's look at this example I've drawn here. We can see that this is tert-butyl iodide. Right? You don't need to know the name, but I'm just, for reference, I'm referring to it. It's tert-butyl iodide. And iodide here is the leaving group. So why is this a good leaving group? Because it's very stable when it grabs the electrons from the bond it has to carbon. You can see the arrow I've drawn, and you can see the iodide is going to grab both electrons from that bond and form a carbocation here and our I minus here. And you can see I've drawn this arrow in red, and I've also drawn the electron pair there in red, right? So you can see how those electrons are being taken by the iodine to form iodide. So why is iodide a good leaving group, right? Because this is very stable. When we remember, if we think about how acidic HI is, right? HI is a strong acid, which means that I minus is a very, very, very weak base, right? It doesn't like to be protonated. And why doesn't it like to be protonated? Because I minus is already very, very happy how it is. It's really, really stable. So that's why, that's one way to think about, it's already very stable, which the acid strength of HI implies that I minus is very stable because I minus doesn't want to get protonated. Right? It doesn't want to form another compound. It doesn't want to react. So that should show you why I minus, why iodide is very, very stable. And that's why iodide acts as the leaving group. So we can see that our carbocation here, I've already talked a little bit about carbocations in the previous video, but since now there's only 3 electron domains, we have sp2 hybridization. And because we have sp2 hybridization, that means we have an empty p orbital. And also, this our carbon is positively charged because, remember, we've basically taken the electrons from the bond connected to carbon and given it to iodide. So now the carbon is electron deficient, and thus must have a positive charge. So one thing I want to mention is that the better the leaving group, right? If this leaving group is good, the more stable this is, basically, more stable the leaving group is, and the more stable the carbocation is, the more stable the carbocation is, right? The more this reaction is going to occur. If we have a if we have more stable leaving groups and more stable carbocations, this right side is going to be overall more stable, and that's going to cause this reaction to occur to a greater extent. So you can see that how I've drawn these equilibrium arrows here is I've drawn them very, very favoring the left side. And this is true, right? Because this carbocation doesn't have an octet, no octet. And just like we talked about with radicals, carbocations are very unstable, right? So they generally want to react. So that's why our arrows, our equilibrium arrows, very, very much favor the left side. But you can think about if our leaving group is a little bit more stable and our carbocation is a little bit more stable, maybe these lines will shorten a little bit, So we have a slightly longer line to the right side and a slightly shorter line to the left side. So that's basically what changes how this equilibrium lies, right? How much it favors the right side. But in general, it very, very much does not favor the right side, and we're just making very small tweaks. When we talk about stability of carbocations, you have to remember that these are inherently extremely unstable compounds. And so when we're talking about a carbocation being more stable, it doesn't mean that it's stable overall. It just means that it's slightly more stable relative to other carbocations. The last thing I want to discuss is that carbocation formation is the first step, and I'm going to talk about this later in the video, in the SN1 organic chemistry reaction. And basically, since we have this positive carbon, right, and it's electron deficient, this is an electrophile. That means that it's electron deficient. So what can happen is we can have this positive carbon attacked by a nucleophile. So if we have this nucleophile has a lone pair, and that lone pair is a site of electron, it has electron, it's electron rich. So this lone pair can go and attack this carbon and form a bond, because this is an electron rich site, the carbon is an electron poor site. They want to come together and form a bond. And so this is really similar to an idea we talked about previously, which is Lewis acid-base adduct, right? So this is a very similar idea to Lewis acid-base adduct. And place with high electron density, and you can think about this as a Lewis base, is going to attack a place with low electron density, which you can think of as a Lewis acid. So now let's discuss radical and carbocation stability. So I talked about stability, I've been mentioning stability previously. Now let's actually think about what is going to cause this to be stable. So first and foremost, the biggest thing is resonance. Resonance is, I've mentioned it as the first bullet point, which means it's the most important, right? If the radical / carbocation can be delocalized, it will be more stable. That's because the radical in carbocation isn't all located, it's not all concentrated on one atom. If it's spread out, it's going to be more stable. If you're sort of sharing the burden between multiple atoms, it's going to be more stable. So let's look at two examples here, right? You can see that we have two examples. So with the first example, we have this carbocation, and you can see that we have a pi bond next to the carbocation, and a pi bond is a site of high electron density, so we can do some resonance with this. We can move our pi bond over, and you can see how the resonance gives us that other compound. So this resonance basically makes the positive charge, the carbocation, sort of spread across two different carbons, which stabilizes the carbocation, right? And here's just one more example. We have an oxygen with a lone pair. So we've talked about these different forms of resonance in my previous resonance video, so I would watch that before you try and attempt this. because I'm just assuming we know what resonance is. So with this oxygen, we have an oxygen with lone pairs next to a carbocation. We can just, donate that lone pair to form a bond with that carbon. And now we have all atoms having octets, right? If we have all atoms having octets, this is much more stable than a carbocation with incomplete octets. So much more stable than incomplete octets, right? When we have octets, stuff is generally more happy. So I've written if we can delocalize it, it's more stable. And if we have an electron donating group, right? Our oxygen is an electron donating group, our radical / carbocation will be more stable. So now let's talk about hyperconjugation. The more R and this just means, when I talk about R groups, that means non-hydrogen groups around the carbocation / radical, the more stable the carbocation or radical will be. Electrons from neighboring sigma bonds can donate electron density. So let me just underline the important parts. The more R groups and electrons from neighboring sigma bonds can donate electron density into the empty p orbital of the carbocation or the half-filled orbital of the radical. So I think this picture really sort of is much better than I could draw myself. So let's look at this picture. Basically, with our carbocation or radical, right, we have this empty p orbital, or with the radical we have a half-filled p orbital. So let's look at this, right? This p orbital is just empty, and so if we can donate electron density a little bit, it can sort of give the illusion of maybe having close to an octet, right? If another orbital, like our sp3 orbital, our sigma bond, so the CH sigma bond is formed by the overlap of sp3 orbital of the carbon and a 1s orbital of the hydrogen, right? So if this sigma bond here this sp3 orbital of the carbon can sort of, overlap just a little bit with the p orbital, we're donating a little bit of electron density. And this is called hyperconjugation, where we have this sp3 orbital of the carbon giving a little bit of its electron density to that p orbital, and that slightly stabilizes it because now our carbocation has a little bit closer to an octet. It's obviously not perfect, but it is more stable than it was before, right? And the more R groups, so if I had the more CH or the more carbons I have next to the carbocation, that means the more sp3 orbitals I have to donate electron density to that p orbital. If we just have a hydrogen though, remember hydrogens only form bonds using the overlap of 1s orbitals. So hydrogens form bonds using the overlap of 1s orbitals. And 1s orbitals, right, they can't do this same sort of hyperconjugation back bonding as our sp3 orbitals can, because our sp3 orbitals are not spherically symmetric, right? They sort of can point in a direction such that they have a little bit of overlap with the p orbital of the carbocation. So hopefully that made a little bit of sense, and it's a little bit confusing to visualize. And there might be better visualizations if you search up hyperconjugation. But the main idea is the more R groups we have around the carbon, the more R groups we have around the carbocation or radical, the more electron density can be donated to that carbocation or radical, and thus the more stable our carbocation or radical will be. So you can see how I've drawn this here. I have the tertiary carbocation most stable, then the secondary, then the primary, then the methyl carbocation. Okay, and last thing I want to say is that so just a general summary is radicals and carbocations do not have full octets, right? They lack full octets. So just a summary to take away, these things lack full octets, and so anything that donates electron density is going to stabilize this. Anything that donates electron density is going to stabilize this, whether it's a pi bond here, whether it's a electron donating group here, whether it's, sigma bonds, whether it's the sp3 orbital overlap, anything that donates electron density is going to stabilize the radical or carbocation. So now I want to look at a question that was on the USNCO, which I thought was pretty challenging and also pretty cool. It has to do with bond strength. So let's first look at the question. Which CH bond has the smallest bond dissociation enthalpy? And we're looking at CHA, CHC, CHB, and CHD. And I've sort of rewritten it in the bottom so it's a little bit more clear. So one thing to note is that bond strength is measured by the dissociation energy, which is homolytic. And when we talked about homolytic bond dissociation, we talked about each atom retaining one electron. So when we think about bond dissociation energy from a homolytic standpoint, we're thinking about radicals, right? And when we're thinking about radicals, if it takes, the more energy if it has a small bond dissociation energy, the radical that's formed is going to be more stable. So think about it like this, right? If the radical that's formed is very not stable or is very unstable, we're going to have to put a lot of energy in to break that bond. But if the radical is stable or semi-stable, we're not going to have to put as much energy to break the bond. So the smallest bond dissociation enthalpy is going to have the most stable radical that we create when we do this bond dissociation. So hopefully that clears up or what you're trying to find is a little bit more clear. So we're basically wanting to understand where is what, when I dissociate, which bond forms the most stable radical. Okay. So let's look at each of these, right? When I take this HA bond here and I dissociate it, I get a radical on the sp2 carbon, right? So it looks something like that with this radical there. If I take my HB, I get a radical here. And you should automatically recognize this from our resonance that I talked about previously, right? We have this pi bond. So if we think about this, right, we can sort of shift this pi bond around using fishhook arrows, right? Let me make that a little more clear. We have this radical is going to donate one electron. We're going to form a pi bond using the, one electron from the original pi bond and our radical. And then we're going to take one electron from that pi bond and make another radical. So let's draw this out. We have a resonance structure that looks like this with our radical there. So we should automatically be thinking, okay, HB looks good. This looks like a good contender, right? We have resonance. And remember what I said was resonance is like the top of the list for stability. So unless anything else has resonance that delocalizes our radical, we know that this guy is going to be the most stable radical because it's got resonance to delocalize the radical nature. So let's sort of initially pick this, and let's look at the other two. The next one is if we dissociate HC. So we look at this, and HC will have a radical like that. And you might think, okay, with HB, when we dissociated it, we only had a secondary radical. But here we have a tertiary radical. And when I talked about hyperconjugation, we were like, yeah, tertiary radicals or tertiary carbocations are better than secondary ones, right? Because we have more sp3 orbitals that can donate electron density and make it more stable. But remember, resonance trumps hyperconjugation. Resonance is better, so HB still wins. And that's why I wanted to make it clear that I put resonance first on my list and then hyperconjugation. Now next, let's look at HD if we dissociated that bond. So I'm just drawing it again here. That would mean the radical is all the way on the rightmost carbon. And now we have just a primary methyl, just a primary radical, which is the most unstable, right? So this is not going to be the best option. The best option is going to be the CHB because, so let's just recap. Why does this have the smallest bond dissociation enthalpy? That's because when we when we break this bond, we form the most stable radical. So our products are the lowest in energy, right, compared to the other three options, which means that our difference in energy is going to be the smallest. Now I want to actually talk about radical halogenation and its importance in chemistry and organic chemistry in particular. So first, the importance of radical halogenation is to introduce a functional group into a compound. And a functional group in organic chemistry is just something we can do chemistry with, right? It's something that's reactive, it's something that has, reactions that we can interconvert and create more functional groups and do interesting things with. So functional groups such as halogens or halides are important in organic molecules. We can interconvert between functional groups relatively easily, but if we only have an alkane, so say we just had, propane or something like that, with no functional groups, it's really difficult to do anything. So to introduce a functional group into an alkane and be able to do cool chemistry, we use radical halogenation. So this can just attach sort of like a bromine or some other functional group. It can attach like a bromine or another halogen into an alkane, and then now I can do some cool chemistry and I can convert between things and I can do all this cool stuff, right? So that's why this reaction is so useful. And just some other examples of functional groups if you're interested. There's ketones, there's aldehydes, there is carboxylic acids, there's ethers, there's amines, there's all sorts of these functional groups. And a functional group just means something that can, that's useful in actual reactions. So now let's look at the actual reaction or the net reaction of radical halogenation that I've written here. So the first thing I want you to notice is nowhere do you see a radical in the reactants or the products. Remember, radicals are intermediates. They're very, very high in energy. They're not going to be isolatable as either a reactant or a product. Next thing I want you to notice is we can see that we start with methane or a normal alkane and we attach a bromine, right? We replace an H with a bromine and we have Br2 as our reagent, and then we form HBr in the end. So that's just like our excess, we want to form CH3Br, we want to introduce our bromine, and our excess material is left in HBr. And the last thing I want you to notice with the net reaction is that we have light as, we need light for this reaction to occur. And what does light do? Light breaks bonds. So whenever we see light, we know that there's some sort of, we need to overcome some energy barrier. We need to overcome this energy barrier to break bonds and form radicals. So we know that this is some sort of radical process. Okay, so now I just want to talk about the big sort of steps of this radical process. You can see I've written initiation, propagation, and termination. Let's think about each of these, right? Initiation, that's like how we said radical initiator. We're just creating radicals, right? The propagation we can think about is our reaction sort of propagating. It's actually happening. So this is the main meat of our reaction, right? We're actually forming cool things. And last of all, we have termination, which means that two radicals combine. So if we have two unpaired electrons, they're going to combine and form a bond, and that's going to pair the electrons. So they're going to combine to form, a molecule. Okay. So now let's look at our two main steps, hydrogen abstraction and halogen abstraction. I'm going to, just describe what these steps are before we go into the details of the mechanisms. Hydrogen abstraction just means we have a radical that pulls a hydrogen off a molecule, and that creates a new radical, because we need to sort of conserve the number of electrons, right? So if I start with an odd number of electrons, then I have to end with an odd number of electrons. So if I start with a radical, I need to end with another radical, right? So we take a hydrogen abstraction just means I have a radical, I have a normal molecule, the radical picks up a hydrogen, and I'm left with a different radical. And halogen abstraction is literally the same thing, but we're talking about halogens. A radical pulls a halogen off a molecule, and that creates another radical. So let's look at specifically each step in our reaction. So initiation, we can see that we have, this is exactly what I showed before. We have a halogen that has a weak bond. So when we have a little bit of light, this bond just breaks homolytically and we form two bromine radicals. Now we have a hydrogen abstraction, right? So this bromine radical and the CH4 are going to react, and this bromine is going to yank off a hydrogen. That's what we have with these fishhook arrows. I'm drawing the bromine forming a bond with the hydrogen. So the hydrogen is taking one of the electrons from the bond to the carbon, and the other electron is going and forming another radical, which forms this methyl radical. So we form HBr and our methyl radical, right? And lastly, we have a halogen abstraction, or lastly in our propagation step, we have a halogen abstraction. So our methyl radical forms a bond with our bromine. It's yanking off a bromine, right? We have a Br2, it's going to yank off a bromine. That's going to form our CH3Br, and it's going to, and then the other electron from our Br-Br bond is going to go to the bromine radical and form another bromine radical. So you can see something about this, right? In our second propagation step, this is important, we form a bromine radical, right? We form a bromine radical. So what this can then go, so when we had our propagation step and we formed our product, right? We just formed our CH3Br. This radical can then go and react again and go back to our first propagation step, right? And yank off another hydrogen, and this can keep continuing. And this is why we call these guys radical reactions. You might have heard of them as chain reactions, right? Because the products, right, my bromine radical, can then go and be a reactant. It can go and react again with our methane, right? So a small number of initial radicals, if I just initiated and I just had a tiny bit of radical, it doesn't matter, because I can then go, because this radical will go and abstract and a hydrogen, and then at the end of the day it's going to form that radical again. So this radical is basically going to go and do the abstraction all over again. So it doesn't matter how much I start with. I don't need to start with a huge amount of radicals, because the radical is formed again in the entire process. And this is why having just a small amount of radicals in our atmosphere and stuff like that can be very, very harmful. You might have heard of, chlorofluorocarbons and why they're bad for our environment. And essentially, it's because it depletes our ozone layer. And why does it deplete our ozone layer? Depleting our ozone layer goes through a radical process. When you're destroying ozone and forming oxygen gas, right? That's sort of a radical process. And these guys, even though there's a very, very, very small amount of them in the atmosphere, when you form the radicals, right, it causes this whole chain reaction. And even forming just a small amount of them in the atmosphere is going to deplete the ozone layer very fast, because just like in radical halogenation, when we use up a radical, we're also producing a radical at the same time in our reaction. So we only need a very small amount of radicals to really cause harm to our environment. Okay, and the last part of our reaction is termination. And this is where two radicals combine to form a molecule. So you can just see every single combination possible is drawn. I've drawn it here. So we have bromine radicals, we have methyl radicals, and we have and we can take any combination of these, right? So here I've shown bromines coming back to form Br2. Here I've shown methyls coming back to form ethane. And here I've shown, our methyl radical and our bromine radical forming CH3Br. So this is just like any combination of radicals if they meet each other by chance. But remember, the reason why our termination steps don't, you might think, right, why are chain reactions a thing? Because even if I form the radical at the end, it should just terminate, right? Because there's other radicals in space. So why doesn't this radical just meet up with another radical and terminate the reaction and stop? Why is chain reactions even a thing? This is because there's so few radicals compared to actual molecules in the in whatever reaction environment this reaction is taking place in. So termination is actually very rare because two radicals need to meet perfectly in order for them to form a bond, but otherwise, and two radicals meeting is very rare because there's not very many of them in the first place. Whereas a radical meeting another molecule, that's not very rare because there's way more molecules than there are radicals. So a radical that's free and just floating around in space is going to meet a molecule, a normal molecule, way more often, and it'll just automatically react because radicals are very unstable and they just want to react with anything and everything that's around them. The last thing I want to talk about is that for a molecule with multiple abstractable hydrogens, so think about here, we only looked at abstracting when we talked about hydrogen abstraction. We looked at methane, right? And methane has 4 equivalent hydrogens. All of the hydrogens on methane are basically the same. But say that we have a molecule with multiple abstractable hydrogens, the one that will be abstracted is the one that forms the most stable radical. So if there were multiple, hydrogens that would form different radicals with different stabilities, right? The most stable radical will be formed because that's the lowest energy pathway, and that'll go the quickest, right? Because everything likes to be lower energy. You don't want things don't like to go over a huge energy barrier. The lower the energy, the easier it is. So things with lower energy are going to form faster than things with higher energy. So if we have multiple abstractable hydrogens, the key thing to note is that the one that forms the most stable radical is going to be formed. So here's an example of that last point I tried to make. We want to look at which hydrogen do we abstract if there's multiple hydrogens that we can abstract. So here I've just drawn our radical bromination conditions. And we know our main things when we look at radical bromination is we abstract hydrogen, and then that radical, that forms a radical, right? This forms radical. And wherever that radical is formed, we add a bromine to that. Because we take that radical, say we have that, radical, and we have our Br2, and remember, this just hijacks a bromine, and we form that RBr, right? That's what happens with radical halogenation. So basically, we want to look at which hydrogen gets abstracted, and then we know that where that hydrogen is abstracted, we just add a bromine there. But which hydrogen is abstracted might not be so simple to figure out, right? So let me look at the first example. I drew this compound here. So remember that they're hydrogens, implicit hydrogens. And when I draw, if I have my radical halogenation conditions, if we abstract this hydrogen, we get a tertiary radical, right? And that's much more stable due to hyperconjugation, what I've written here. So the most stable radical is tertiary. Say we took a different hydrogen and tried to abstract that. Say there's 2 hydrogens here. So say we took one of these hydrogens and we abstracted it. Then we would get a secondary radical, and that's not as stable as a tertiary radical. So this is not going to form as easily as our tertiary radical, and so this is going to be our main product. Our main product is going to be our tertiary radical, and that tertiary radical is going to immediately abstract the halogen and attach a bromine there. So that's why we form this compound. And one more example is if we had a phenyl ring, and we had a methyl group coming off of that phenyl ring, we want to abstract the most, the most stable. We want to form the most stable radical. And if we abstract the hydrogen coming off of the methyl, right? Let's look at the radical we create. We would create a radical that looks like this, right? With our radical right there. And you can see that we have all this resonance that can happen with that radical. We can basically delocalize this radical all around the ring, and here's one way we can do that, like that, right? So you can see that, and then from here, now that our radical is there, we can delocalize it even further, and we can do this all around the ring. So basically, this is a huge amount of resonance, right? So this is going to be very stable comparatively, right, as a radical. So because this is very stable as a radical, this is going to be the radical that's formed, and that's where the bromine is going to be attached. So this hopefully, gave you an idea of, you want to look at resonance and you want to look at hyperconjugation, right? When you're looking at most stable radicals that can be formed. So essentially the idea is, when you abstract the hydrogen, you want to form the most stable radical, because that'll be the lowest energy pathway, that'll be what happens the quickest, that'll be what actually happens, right? You always want to do something that's easier than do something that's harder. So lower energy pathways are always favored. And the last thing I want to go over is SN1 reactions, right? And again, I mentioned this when I talked about carbocations, but now I want to go into it a little bit more in depth, but not super more in depth. This is just one class of substitution reactions. The other class of substitution reactions is SN2. I've sort of mentioned this a little bit, but not, I haven't gone super into depth in organic chemistry topics. But I just wanted to show SN1 because it has to do with carbocations and carbocation stability, right? So basically, we have two steps in SN1 reactions. There's two steps. The first step is our leaving group leaves, forming our carbocation, and we saw this in the carbocation slide, right, where we had an iodine just leaving with the electrons and forming a carbocation. That's essentially what happens in SN1 reactions. But then we have one extra step where a nucleophile attacks our positively charged carbon. So just like what I drew here, I drew this exact same thing on the other slide, right? Our iodine leaves, and now we have low electron density in our carbocation. And say this is in a water solution, right? Say this is in a solution of aqueous solution. If this tert-butyl iodide is in an aqueous solution, there's water all around it. So for iodide leaves, this water, right, the oxygen in water has a lone pair. So this lone pair can go and attack our carbon, because lone pair implies that there's a high electron density on that oxygen. And because this carbocation doesn't have a complete octet, it's electron deficient, we have low electron density on our carbocation. So this oxygen, from our water, can go and attack our carbocation and form a bond. And so we get this, right? That's just what happens when I take my, I take my lone pair on my oxygen and I go attack the carbocation and form a bond there. And finally, we have a deprotonation step that occurs. So another water molecule might come in solution and deprotonate, right? Deprotonate that OH2, and that forms an alcohol. And because we had a deprotonation step, we also formed H+, right? And we formed our iodide just like before. So this is generally just what SN1 reaction is. We have the leaving group leave, and then we just have a nucleophile attack. So that's essentially what an SN1 reaction is, and I thought it was relevant because it sort of gives you an idea of where you see the carbocations in actual mechanisms. So why is this a 1 in SN1, right? And this stands for first order kinetics. So when we saw our 2 in SN2, that stood for second order kinetics. So let's look at why this is first order kinetics. If we look at a rate determining step, right? When we look at kinetics, we always want to look at our rate determining step. What is the slowest step? That's going to be the step where the rate law actually matters, right? So let's look at the slowest step. The slowest step is going to be the one where we go from a lower energy to a really, really high energy. The one with the giant activation energy barrier. So if we look at our energy diagram, right? If we have some energy diagram like this, this is going to be our rate determining step, this A to B. This is going to be rate determining step because B is way higher in energy than A, and thus we have a huge activation energy barrier to get across, and that makes it slow, right? Big activation energy means it's going to be a slow reaction. So what has really high energy? Carbocations have really high energy. So this step is basically B in this diagram, and A is our initial reactants, right? So our first step, that I've drawn here, this first step, is the slow step because we form the carbocation. And our second step, where a nucleophile attacks our electrophile or attacks our carbocation, is very, very fast. It's very fast because this carbocation is super unstable. There's high electron density on the water. So it's just going to attack very quickly. We have this sort of polar attraction, right? We have a positive charge on the carbon, electron density on the oxygen. There's just going to be an attack because that's going to lower the energy of the system, dramatically. Because now everything will have octets, right? So what I wanted to get across is that our first step is going to be our slow step. So what does that mean, right? The slow step is going to be the formation of carbocation. And so if we look at our reactants for our, for the slow step, we only have one reactant, right? We only have one reactant. So if I think about writing my rate law, I have rate equals K, whatever my K constant is, times the concentration of my reactants, which is just one reactant. And so here we can see that this is first order. We only have one reactant, so it's a first order reaction. And that's where we get the 1 from SN1. And in SN2, we have basically the idea, the gist is that we have the nucleophile attacking, and the nucleophile attacks the initial substrate in the first step, right? There's no formation of carbocation, and there's no, subsequent nucleophile attack. Instead, the nucleophile attacks and the leaving group leaves all at the same time. So we have two different things in our rate determining step. We only have one step, so that step is our rate determining step. So in our SN2 reaction, right, we have rate equals K times the nucleophile is also included, right, because that's attacking the substrate in the first step, times our actual substrate. So if this was a first SN2 reaction, we would have this nucleophile also in our rate law. But because it's SN1, we don't have the nucleophile because that's the fast step. The slow step is just the carbocation formation. And you can see with SN2, we have, it's a second order reaction because we have nucleophile and our substrate. So that's where we get SN1 and SN2. That's basically just from the kinetics of the reaction. So this is all I wanted to go over in this video. I hope this was informative to you. I know it was a long video, but I hope you got something out of this video. Thank you guys so much for watching, and I'll see you in the next one.